Find the heat loss per square meter of surface area for a furnace wall 25 centimeter thick which has inside temperature of 1050 degrees centigrade and an outside temperature of 50 degrees centigrade. Thermal conductivity of the wall is given. K is equal to 1.1 plus 0.00116 T watt per meter degree centigrade, where T in degree centigrade. This is the variation of thermal conductivity between inside and outside of the cylinder. And here the options are 6.954 kilowatts, 7.92 kilowatts, 5.954 kilowatts, and 8.92 kilowatts. So here we'll have to find out the heat loss per square meter of surface, and is given by, let us say, Q dot is given by delta T by thermal resistance of the system. Here delta T is the change in temperature between the outside and inside of the cylinder, and thermal resistance 1 can be obtained by using the formula del X by K, where del X is the thickness of the furnace and K is the mean thermal conductivity of the material and A is the surface area, and here surface area is given by 1 square meter and thermal conductivity variation is given by 1.1 plus 0.00116 T. So here it varies linearly from outside to inside, so that we can take the mean temperature between the outside and inside of the furnace, and we'll have to find out the mean thermal conductivity, that is 1.1 plus 0.00116 T is the mean, that is 1050 plus 50 by 2, so which is equal to 1.738 watt per meter degree centigrade. Now substitute this value in thermal resistance, which gives del X is 25 centimeters or 0.25 meters, and here it is 1.738, which gives a value of 0.1438 degree centigrade per watt. And heat loss to the wall is given by delta T is 1050 minus 50 by 0.1438. So gives a value of 6954 watts or 6.954 kilowatts. So here the right answer is 6.954 kilowatts, and in the option the correct option is A. A is the right answer. A system undergoes a process during which the heat transfer to the system per degree increase in temperature is given by dQ by dt is equal to 2 kilojoule per degree centigrade. The work done by the system per degree increase in temperature is given by dW by dt is equal to 2 minus 0.1 T. If during a process the temperature of water varies from 100 degrees centigrade to 150 degrees centigrade, the change in internal energy will be. The options are 125 kilojoule minus 250 kilojoules, 625 and minus 1250 kilojoules. So first consider the heat transfer to the system, that is dQ is given by 2 dt. So here the temperature varies from 100 degrees centigrade to 150 degrees centigrade. Let us say T1 is 100 degrees centigrade initial temperature and T2 is final temperature, that is 150 degrees centigrade. So here change in heat transfer to the system, Q is equal to 2 into T2 minus T1, that is 150 minus 100, so which is equal to 100 degrees centigrade, so 100 kilojoules. Now consider work transfer, that is given by 2 minus 0.1 T into dt. Now consider the work done during a process when temperature changes from 100 degrees centigrade to 150 degrees centigrade, which is given by W2 to 1 is equal to 2T minus 0.1 T square by 2 from 100 to 150. So which gives 2 into 150 minus 100 minus 0.1 150 square in minus 100 square by 2. So here it comes at 525 kilojoules. Now the change in internal energy for a system is given by energy is equal to Q minus W. So which is equal to 100 minus 525. So is equal to 625 kilojoules. So the change in energy of this of a system is equal to 625 kilojoules, and in the options the right option is C. C is the right answer. Consider an arrangement in which a wire coil of a good conductor of heat is placed in a position as shown in the figure. What will be the effect of placing this wire coil? Here, this is the given diagram. A flame is in between a coil. A flame is surrounded by a coil which is a good conductor for heat. Here the options are: the rate of combustion will increase rapidly, the flame will be extinguished, the wire coil will melt, the brightness of the flame will diminish. Here we can eliminate directly two options. One is the rate of combustion will increase rapidly. Actual rate of combustion doesn't depend on the surroundings, so that we can eliminate A. And coming to the next, the wire coil will melt. We don't know the melting point of the wire or melting point of the that metal of the wire, so that we cannot say that the wire coil will melt. And the remaining two options are: the flame will be extinguished and the brightness of the flame will diminish. Here brightness also not depending on the surroundings of the flame, so that it is not also correct option. So the correct option is the flame will be extinguished. That means it will be destroyed after some time due to the surroundings, due to the encountering of that coil. So the correct option is B. B is the right answer. A vapor compression refrigerator operates between minus 15 degrees centigrade and 10 degrees centigrade. The actual COP is one third of the ideal COP and power input to compressor is 25 kilowatts. Calculate the cooling effect. Here the options are 56 kilowatt, 66 kilowatt, 76 kilowatt and 86 kilowatt. So coming to the solution, here the given actual COP is one third of the ideal COP, and ideal COP of a VCR is given by T2 by T1 minus T2, where T2 is the lower temperature and T1 is the upper temperature. Here T1 is equal 283 Kelvin, that is 10 degrees centigrade, and T2 is equal minus 15 degrees centigrade or 258 Kelvin. So here ideal COP of the cycle is given by 258 by 283 minus 258, which is equal to 10.32, and actual COP of the cycle is equal to one third of the ideal COP, that is 10.32. so that here 10.32 by 3 is equal to 3.44, and the COP of a VCR is the ratio of cooling effect to power input or refrigerating effect to power input, that is actual COP is equal to cooling effect or refrigerating effect by work input or power input. So here power input to the compressor is given by 25 kilowatts, and cooling effect of the cycle is equal to 3.44 into power input, that is 25, which is equal to 86 kilowatts. So here the correct answer is 86 kilowatts and the right option is D. D is the right answer.